Hey everybody, welcome back to Calc 3 Online. So this is going to be our second review video here. And one of the big things from this year definitely is the optimization techniques for multivariable functions. There's just tons of stuff out there in the world where we're just trying to optimize something. So we're trying to find a maximum or minimum of some sort of surface or whatever. And one of the kind of trickier I think more conceptually tough ones to think about that we did this year is the Lagrange multiplier ones. So these are a little bit different because what we're doing in these problems is we're still maximizing this function, but we're maximizing on a constraint. So what I mean by that is, this thing right here, if you graph it, I'm not going to do a good job, but it basically looks kind of like kind of a hyperbolic saddle surface thing, something kind of like this. Oops, I went the wrong way with that one. Kind of like that. So this is like a saddle in here. That's a horrible picture. You should just graph it and take a look at it. But what we're thinking of is you have some sort of surface, okay? We're maximizing it on a constraint, and if this thing I can easily explain, that in like 2 dimensions, it looks a lot like a circle, but it's when you do x to the 4th plus y to the 4th, basically it looks more like a square circle. It's kind of like you almost take a rectangle or square and then you curve the edges. So it sort of looks something kind of like this. It looks like that, and it's the idea is like we think of maximizing this object on this constraint. So you kind of think of honestly actually this thing down here, and then you sort of project it up, and so we're thinking of it around the surface, if that picture makes some sense. Pretty horrible picture. This surface is going to have some sort of attain some maximum and minimum value while you move along that path. The way I always think about these things are basically like, maybe this represents some mountain or whatever, and you want to figure out like if we're going to cut this new road or something on this mountain, like what point on the road is like maximum height or minimum height, those kind of things, like how high really are they and whatnot. So you can kind of think it could be a useful thing to know given some sort of constraint, what is the highest and lowest value. We also talked about these regarding economic problems, and I remember seeing a bunch of those where your constraint might be some sort of like profit margin function. And this dictates like kind of the parameter that you can work within based on like your ad revenue and all this other stuff. Like this is kind of like what you can get or something. And then we look at it based on, the overall model. And then we kind of think, okay, well, what's the best we can do on that model, that kind of thing. So that's sort of the idea. The way we do these problems, which is really the main important thing here that I want to make sure you know, is you're basically solving a system of equations. And I'm not going to get into in this video like the theory behind how it all works. I did that in like another video. You can go back and look. But basically, if I think of this thing as G and this thing, is defined as F, it turns out to be a gradient problem. You basically have to solve the following equation here. Gradient of f needs to equal, we use lambda, but it's really just like a scalar. Scalar. And then gradient g. And this would give me, I have a variable lambda, and then I'm going to have x and a y. So I've got 3 equations there, or 3 unknowns. So I need a third equation, and we've got to keep it on the path that we're, sort of acting as the boundary thing here. And so we need to include that constraint function as one of my equations. So this will give me a few equations. It'll give me two. And then I'll have another one from there. So I also have the equation 3x to the fourth plus y to the fourth equals 1. And so that's it. So, specifically what this part becomes, the gradient of f would be 3x squared y, and that needs to equal lambda gradient of g, and like the x component of the gradient, right, needs to match up. So that would be 12x cubed, just be 12x cubed, right? Then I need the y component to match up on both sides. So that gradient of f would be just x cubed, needs to equal lambda, and then 4y cubed. So this equation, and this equation are really what I use to solve these things. And so now you really just are solving systems of equations, and you can run into some weird algebra and stuff for sure, but this is where you just kind of rely on your algebra skills, really. So the way I think about this one, you can kind of treat it in cases. One case is like we can think, okay, what if x equals 0, right? And the other case we can think of is what happens if x doesn't equal 0. And that's the only possibilities for x. So if we can kind of answer the problem with those two, we've actually done it, right? We solved the system still. So it's just easier this way because it's going to do some nice simplification for us. So if x equals 0, notice here and here and here, you have, that first equation is satisfied. The first equation is satisfied just trivially, right? Because you have 0 equals 0. But here, x equals 0 in the second equation, so maybe I'll just do it like this. Second equation would imply that lambda has to equal 0, right? And then if lambda equals 0, if we go on to the third equation, we don't know anything about y per se. So in the third equation, it would imply that just, this part would equal 0, but then y to the fourth would equal 1, or y would equal plus or minus 1, right? Those would be the two ways to make that work. So this is basically giving me points like the form 0, comma, plus or minus 1. So these are some things I will have to check for the maximum minimum part here. The other kind of case is just thinking, well, what if x doesn't equal 0? And this is nice because we have like x's on both sides here. So we can divide by x now, or x squared, right, because it doesn't equal 0. And so if I also divide by 3, in that first one, equation 1 would just become y equals lambda, let's put the 4 in there, 4 lambda x. And then I could plug that in to the second equation. And if I do that, I'm going to have x cubed equals lambda 4, and then I'll put in my y, which is 4 lambda x, okay? And then all of that is cubed, right? And now you can just go and simplify some of this stuff. You would simplify it down to, so some stuff that's nice. You got an x cubed on both sides. That'll go away. You've got 4 cubed plus another one is 4. That's 4 to the fourth. You've got lambda to the fourth. So it's looking like it's going to simplify to 1 equals lambda to the fourth, 4 to the fourth. And so if you solve for lambda looks like it's going to be plus or minus 1/4, okay? And then from there, I can get y in terms of x if I just go back here, right? Because I've kind of eliminated what lambda is. Lambda equals plus or minus 1/4. So this is sort of saying, so this part and this part together say that y equals plus or minus x. And then that's nice, kind of gotten rid of lambda there. So I can go to here. I haven't used this thing yet. If I plug in, let's just plug in what y is, right? So we'll have 3x to the fourth plus, it's y to the fourth. Y is plus or minus x, so it's just negative doesn't really matter. And then from that, you're going to get 4x to the fourth equals 1, or x to the fourth equals 1/4, or you're going to get that x equals, what would that be? Plus or minus 1 over root 2, right? Because 1 time be plus or minus a half, and then plus or minus root 2. Okay. You have x is plus or minus 1 over root 2, y is plus or minus x, right? So this is enough to get my final point here, or final points, I should say. Basically, the last few points would look like this. It'd be like 1 over root 2, comma, plus or minus 1 over root 2, and then negative 1 over root 2, plus or minus 1 over root 2, right? And so you got quite a few points to check. You got 1, 2 here, another 2 here, and another 2 here. And then whenever you do these Lagrange multiplier things, you just go, once you get your points, that's usually like the bulk of the work, then you just got to go and you go to f of xy here. Basically, these should all live on that constraint. We've used it in solving the system. And then we just go plug it in, and we see literally which thing is the highest and the lowest value. And I'm not going to go through plugging them all in. It's kind of boring. Some of them are not so bad. If you plug in, this here, you're going to get 0. So these ones are actually where the maximums and minimums happen. If you just go and test them all, basically, turns out that f of, I'll just write it down here. So these 2 points give you 1/4, and these 2 points give you negative 1/4. And those are the maximum and minimum values that you can get on this function given this constraint. That's kind of a good example of Lagrange multipliers. It's a very, very commonly used technique for optimization stuff. There's just so many things out there where we need to optimize a surface given some sort of graph or whatever. And there's even other versions that we didn't get into in the text. You can see them, but these are kind of the basic ones that you want to make sure you understand. All right, a little more straightforward problem this time. Another really important thing we did this year is just line integrals, all right? It's important that you can look at an integral and kind of see that this is a line integral. Whenever you have like the dx, dy thing, there's a line integral being involved. It's also important to know that this is basically like the f dot dr, where this kind of bold type of line integral. So we're thinking some sort of vector field basically is involved here. Dr is basically the vector here, dx, dy. And if you dot, this stuff in front, like this, comma this, with dx, dr, you get this thing right here. That's a line integral. So basically, I really think of them as curve integrals. This one I can actually draw pretty well. We've got a point at 1, 1, and we've got another point at 3, 2, 1, 2, 3, and negative 1, about back there. Here it's actually like a line integral, but if you think of this drawn down in the plane, it is a line, and we're literally just sort of curious about the interaction with the field and as we move along the path from specifically this point to this point. But a lot of times this path is not a line. It's like some sort of weird, curve down here. We've seen a lot of ones where it's a closed loop. If it's a closed loop, That's when you introduce that little symbol to just kind of tell the reader, hey, you're going around a closed loop. Very, very commonly used tools in math and science. So to do these things, we got to parameterize stuff. So we're parameterizing a line. So it kind of goes back to chapter 12 stuff. A line here could be written as a point on the line, 1, 1, plus t times, it's kind of like your slope vector in here. So 3 minus 1, it's 2, and then negative 1 minus 1 is negative 2. So that kind of tells you, like, really what you've done is you've sort of seen the change in x and then the change in y as you move from here to here. So it's like a slope, right? So this tells me that x equals 1 plus 2t. Oops, that's bad t. And y is 1 minus 2t. And then this kind of line integral, we need dx and we need dy. So dx is going to be 2 dt, and dy is minus 2 dt. And then literally you have x, y, dx, all the dy there too. You got everything you need to plug in. And so we can plug in everything. We got 1 plus 2t plus 2 times 1 minus 2t is y. Let's see, so then I want to multiply by 2 dt right there. And then moving on to kind of the next term, I guess. X is 1 plus 2t. Erase that. And then 2 times 1 minus 2t is y. And then dy is minus 2 dt. And in terms of bounds, right, notice that if you plug in 0 for t, you'll start at 1, 1. So that's where we are starting. Direction here is important. This kind of line integral, the direction is going to matter. The ds one is where it doesn't matter. Then if you plug in 1, right, notice 1 plus 2 is 3, and 1 minus 2 is negative 1. So if you go 0 to 1 on this integral, you'll have it. And so then it's just like a ton of simplification, and actually it's all pretty nice integrals from here. So if you simplify it down, you'll get this. So we get that after you simplify everything down, and then actually it turns out to be a really nice integral, because if you do that out, you get 0. So yeah, that's kind of line integrals in a nutshell. I mean, that's really just kind of one kind. You'll see them written this way for sure, and you'll also see line integrals with respect to ds, and when we do that, we're just thinking about, like, really more the idea, if I kind of utilize this picture a little bit, if you do the ds ones, you've got like some sort of path or whatever, and we're truly just thinking about, how much area is there, like above or like below this path and to some sort of, surface up above or again below. And so these kind of ones, you're looking at more just kind of a signed area above or below that path. And and it does not matter in the DS ones whether you go this way or go this way. But this one, any of the dot product ones, they do matter. All right. Just another really important thing from this year, that's going to be the last thing in this video, is multiple integrals. You need to know how to solve, double, triple integrals. And, the way I would do any of these problems is I would start by setting up the region. So when I solve any of these, I think really just like XY space for a second here, and I'm just thinking, what do these bounds tell me I'm integrating over? Because that's going to dictate whether I want to do like a change of variables or something like that. So this bound, right, is saying x equals negative square root of 9 minus y squared. This is x equals 0. X equals 0 is just the y-axis. That one's nice and easy. This one, if you think about it, anytime you get a x equals a negative square root, and there's some 9 minus y squared in there, that's like a circle thing. And it's just, I mean, it's a half circle, really. It's specifically the half circle right here. The 9 in there tells me I have a radius of 3, so that's out at negative 3. This is up at 3, and this is also down at negative 3. And then it kind of checks out with the y bounds, right? I'm going from negative 3 up to 3. And so this should be like a clear cut. This is what I'm integrating over. This is like a clear cut polar problem. So, you know, I should switch to polar. So x squared plus y squared is going to be r squared. And then the Jacobian is the RDR d theta part. So that is kind of what an area element looks like in polar, right? And then in terms of bounds, r is going 0 to 3. The radius, right, is just 3 everywhere in this circle. And then theta is pi over 2, right, up here, to 3 pi over 2 down here, right? Just map that out. Pretty nice integral to solve. It's a u sub. Let u equal r squared plus 16. du is going to equal 2rdr. 2rdr. So then you can pop that in right here. And you could take out... this is one where actually there's going to be nothing involved with the angle too. So you can also just kind of start and think you're going to have a 3 pi over 2 minus a pi over 2 as like a scalar on this integral. That means there's a pi scalar, right? 3 pi over 2 minus pi over 2 is pi. So you basically have a 2 to pull out and a pi from that. So I could jump and simplify this all as 2 pi now times 0 to, well, I'm switching to u, so I'm just going to leave those bounds for a second. Square root of u du, and I did the d theta already. And so then it's just going to be like, you got a 1/2, raise it to a 3/2, divide by 3/2, or multiply by 2/3. So I'm going to multiply by 2/3 in front there. Oops, I just did the integral. Then I'm putting r squared plus 16 back in, and then I will have to do that from 0 to 3. Whew, there we go. So if you do that out, this is all fairly nice stuff in here. If you do that out, you'll get this. Yes, you get 244 pi all over 3. So that's a good example of one where you would want to use polar. Oh boy, just looking at it right before I moved on to this one, I just saw that I put a 2 here, and I think I said that too. I'm being too lazy. So du is equal to 2rdr, right? But I have rdr, so I want to divide by 2, not times by 2. So I would have a 1 over 2 there, a 1 over 2 there. And so it's going to change some of this. I should have just 61 pi over 3 in there instead. So sorry about that, but a lot of the other stuff is correct there. All right, so for this last one, let's draw it first. I think this should be enough room. I'm going from, in y, I'm going from y equals 0, which is, of course, the x-axis, up to y equals x plus 1. So let's say that's 1, 1, 1, okay. It's going to go like that. And then I go from -1 to 1 in x. So I get like another cutoff right there. So the region on this one is sort of this triangle right here. And, you know, some important points. This is 1, 2. This is -1, 0. This is 1, 0. So yeah, we're integrating over that triangle with those vertices. And this is a good one to go over because it's one of these where if you do dy first, it looks like a kind of a disaster, but it's one where if you do dx, it's going to be much easier to solve. So the dx integral is just super nice because there's literally no x's in here, right? And so I would switch the bounds. And it's not a bad one to switch the bounds because you have a triangle, and you can do triangles as type 1 or type 2. Right now it's set up as type 1. Basically, you know, I still have 4 y minus y squared, all of that still in there. But if I do dx dy, I just switch the bounds. So dx would go from y minus 1 to 1, and then x would go from y minus 1 to 1, and then y would go 0 to 2, right? And then you just, if you do the dx integral, right, you're just going to tack on an x, and you're going to do like 1 minus y minus 1 in there. And so you're going to go and get a 2 minus y times 4y minus y squared to the 3/2 dy. And actually now, it's a pretty nice u sub. So if you do u equals 4y minus y squared, that's basically how I'd go about solving it. I think you guys can kind of get it from here, so I'm just going to write down what you should get. You'll have like a fifth, 4y minus y squared to the 5/2, going from 0 to 2, would give you 32 over 5, if I did my math right. I think I did. So these kind of just represent two important techniques for multiple integrals, switching a polar or doing a switch of the order of integration. Either way, I start by graphing.